Previously, we learned about arithmetic sequences, which differed by a common difference for each term to go to the next term, and now we're going to look at geometric sequence. The idea behind geometric sequences is to get to the next term, you have to multiply by some constant multiple. So I would start at my first term, and then to get to the next term, I would just take the first term times my common multiple, which is called the common ratio r. To get to the next term, I'd multiply by r again, so it's equivalent to a1 times r squared. To get to the next term, I multiply by r again, which is equivalent to a1 times r cubed. So since the common ratio just keeps getting multiplied by the previous term, we can write all terms in a geometric sequence as some relationship between the first term and some exponent on the common ratio. So the formula for the nth term of a geometric sequence is always the first term times the common ratio to the exponent n minus 1. So here we're told that we're dealing with a geometric sequence. Immediately that tells us to get to the next term, I multiply by a common ratio. And I'm told the first term is 5, and the common ratio is -2. And we're asked to list out the first four terms. So we'd start at 5, and then we'd go to the next term, which is 5 times -2 would give us -10. Then to get to the next term, that's -10 times -2 gives me a +20. To the next term, 20 times -2 gives me a -40. And this could all be written out as my first term. This is my first term times the common ratio. This is my first term times the common ratio squared. And this is my first term times the common ratio cubed, because that's 5. 5 times -2. -2 squared is 4, times 5 is 20. -2 cubed is 8 times 5, or sorry, -2 cubed is -8 times 5 gives me -40. So if we wanted to write a formula for this geometric sequence, it would be the nth term is always the first term times the common ratio raised to the n minus 1 as the exponent. And particularly when your common ratio is negative, I encourage you to write it in parentheses to show that this whole thing is being raised to the n minus 1 exponent. Now for our next example, we're told that we're dealing with a geometric sequence, and we're given the first term and the fourth term. But we do not know the common ratio, and we're asked to find the second term. Now what I could do is I could write out the terms that I know. I know the first term is 3. I don't know the second term. I don't know the third term, but I do know the fourth term is 24. And then what do I know has to happen? To get from here to here, I multiply by the common ratio. To get from here to here again, I multiply by the common ratio. To get from here to here, I multiply by the common ratio, and I'd get 24. That would give me the equation 3 times the common ratio. It multiplies by itself 1, 2, 3 times, so the common ratio cubed equals 24. And the great thing is, once I know the common ratio, I can multiply that by 24 to get the next term, or I can multiply it by 3 to get the second term, which is what I'm looking for. So I'm going to divide both sides by 3. The common ratio cubed equals 8. And then we think, what's the cube root of 8? That would be 2. So our common ratio is 2. That means that the next term would be 3 times 2, which would give me 6. 6 times 2 gives me 12. And then 12 times 2 definitely gives me 24. So that works out. So the A2 that we are looking for is 6. Now if you prefer to go through this by a more formula-driven approach, what you could do is you could write out the general formula for a geometric series. Right now there's 1, 2, 3, 4 things that are representing by things we don't know. We actually know a sub 1, so let's substitute that. And then we'd need to know the common ratio to find the next term. So we're going to use this as a key. This means when n is 4, a sub 4 is 24, so we can write out 24 equals 3 times the common ratio to the 4 minus 1 That gives me 24 equals 3 to the r cubed. We get the exact same equation as before, just through a slightly different approach. We divide both sides by 3, take the cube root, and we get the common ratio is 2, which we then multiply by 3 to get the second term of 6. So our key thing here is we took the phrase geometric sequence, and we knew that that means that these terms differ by a common ratio, which allowed us to solve for the unknown value. Here we're asked to write an explicit formula for the nth term of the geometric sequence. We know in general it's a sub n is the first term times the common ratio to the n minus 1. So that tells me if I know the first term and I know the common ratio, that's all we need. The first term is just the first term written, that's nice. And then the common ratio is how much they differ by how do you get from one to the other as a multiplier. So we think 2 times what gives me 10, that would be 5. Let's see if that holds. 10 times 5 is indeed 50. 55 times 5 is indeed 250. So the first term is 2, the common ratio is 5. Therefore, a general formula is 2 times 5 to the n minus 1. I'd encourage you to pause the video and work through this one on your own as well. Remember that we do have a general formula. We know that a sub n is the first term times the common ratio to the n minus 1. So you can write a general formula if you can identify the first term and if you can identify the common ratio. So attempt the problem, pause, and then unpause to check your work. Now we know the first term written is a sub 1. And then we think, since we've been told this is a geometric sequence, we know they should have this constant multiple relationship. Negative 1 times what gives me 3? Well, since it's negative and I end up with positive, it's going to need to be negative. And specifically, negative 3 should work. Negative 1 times negative 3 is positive 3. Let's see if the pattern holds. 3 times negative 3 is negative 9. Negative 9 times negative 3 is positive 27. Positive 27 times negative 3 would be negative 81. So the sequence is holding so far. So let's say our common ratio here is deciphered to be negative 3. And in this case, these were nice multiples that we're probably used to. But if it was ever a little bit more obscure, you could always find the common ratio by taking the next term and dividing it by the previous term. Negative 9 divided by the directly previous, or 27 divided by the directly previous. In this case, all of these would give you the value negative 3. So if the pattern in the terms is not as clear, take the next term and divide it by the previous, and that should give you the common ratio. Now that we have the first term and the common ratio, we know the formula says the nth term is just the first term times the common ratio raised to the n minus 1. So as we're remembering geometric sequences, we know geometric sequences have a constant multiple, and arithmetic have a common difference. So in arithmetic, you add a constant term each time to get the next term. In geometric, you multiply by a constant term each time to get the next one. In both cases, we know a general formula that if we can find for the geometric case the first term and the common ratio, then we can fit it into this formula. And we have a similar formula for arithmetic that deals with the first term and the common difference.